Thank you very much for the introduction, and thank you to all the organizers for inviting me to give a talk at ODSC West this year. As mentioned, my name is Petar Veličković. I'm a staff research scientist at Google DeepMind and affiliated lecturer at the University of Cambridge. And today I'll be talking to you about an area of artificial intelligence and machine learning that I am personally most excited about in recent times, and it concerns graph representation learning. What I usually like to say is we're going to have a nice discussion about graph representation learning, and hopefully by the end of this discussion, you will realize that really we should all be doing graph representation learning. Sounds like a potentially big ask. Let's see how far we can get in actually making this claim realistic. So really, let's start from the first question that we want to ask ourselves, which is, why should we bother to study data on graphs? Why should we bother to make machine learning models that operate over graphs? Well, if you ask 100 different people that do graph representation learning, why are they doing it? They might give you different answers. For me, it really starts at the core of data. So machine learning really is all about making sense of large quantities of data. And when you think about data that comes from nature, it is really most of the time irregularly graph structured. And you can see this at all levels of organization of life, starting from the most rudimentary building blocks like the molecule. Molecules are typically realized as a interconnected graph structure of atoms connected by chemical bonds, all the way up to the highest levels of organization, like the connectomic structure in the human brain, which is very nicely representable as a graph of neurons connected by synaptic connections. But really, graphs appear not only in data that we receive from nature, they're also quite omnipresent in social constructs and constructs that we synthetically make as humans. So one very popular example of this is the transportation network. Here on the upper right, you have a slightly outdated picture of the London tube map, which you can very naturally represent as a graph structure of various underground stations and the links connecting them. And also maybe one that is industrially most popular example of graph structured inputs in the wild is the social network. So here you have the Facebook friendship graph from a few years ago, where social networks can be nicely represented as a graph of humans connected by friendship links. And naturally, I think that both scientists and practitioners have started more and more to take on this impression that their data really is actually graph structured under the hood. And that's why in the last few years, graph neural networks, the flagship representation learning model that works over graph data, has truly taken the world by storm and is now applied virtually everywhere. I have given here just a sample of a few of the applications that I'm personally most enthusiastic about. One of my favorites is this work for scientists from MIT that have used graph neural networks to discover a new powerful antibiotic. Then many companies, as I said, leverage the social network and the graph of different users and different content that they might interact with. One example of this is Uber Eats, which has notably published a blog post declaring how they use graph machine learning to recommend which food you should eat next. But it's not just Uber Eats. Pinterest uses them to recommend which content you should interface with next. Airbnb uses it to recommend which place you should stay in next. Amazon uses it to recommend which products you should buy next. So it's really omnipresent, and it might be driving decision making in more humans day to day, like you might be interacting with graph machine learning without even being aware of it. And this is where one of my own personal claims to fame comes from as well. As you can see in the top right corner, I was part of this team from DeepMind that has built a graph neural network system that is currently deployed inside Google Maps and serving travel time queries. So basically, you can go into Google Maps wherever you are, type, I want to go from A to B, and the system will usually offer you a few routes, and for each route, you will get an estimated travel time. That travel time is now everywhere in the world served by a graph neural network that we have developed inside DeepMind. And as another interesting example, Google AI has recently used these graph neural networks to help design its latest generation of artificial intelligence chips, the TPU v5. Which I think is a really nice circular argument where AI powered by graph neural networks designs the next generation of hardware used to train the next generation of AI systems. And while you might claim that some of these references are potentially outdated, here is just a quick set of references showing that graph neural networks are very much still everywhere. All of these references are from the year 2023. There has been another breakthrough drug discovery using these models, which has been published in the MIT News and otherwise. They are extensively used in particle physics at the Large Hadron Collider in Switzerland. There is now a review paper detailing exactly how they're used there. Then a paper using GNNs recently landed on the cover of Nature Machine Intelligence through a very interdisciplinary team spanning folks from the University of Cambridge. And also in a recent publicized science paper, graph neural networks were used to detect smells of various molecules, which is something that could revolutionize the perfume industry and similar industries. And if you look at a signal from the world of research, graph machine learning and graph neural networks are still among the top trends and top keywords in top machine learning conferences like ICLR. And specifically, it is still a more commonly cited keyword than even the transformer. Recently, we have also used these graph machine learning models to help mathematicians discover intricate structures of mathematical objects and then use it to settle long-standing conjectures and problems in areas of math as diverse as knot theory and representation theory, which is a feat that landed us on the cover of Nature in December 2021 and also receiving significant media coverage. So really, hopefully the past few slides motivate you that graph neural networks and graph structured data are really omnipresent, not only as a kind of hypothetical data point, but really as something that is being applied already all across industrial applications, all across scientific applications. And really, whenever your data is irregularly structured, using a graph abstraction might be a good idea to deal with it. And really, you can even go beyond this and talk about how our very process of cognition is graph structured, right? You never recall every single experience you ever had when you need to make a decision. Rather, your brain recalls specific important concepts, how they relate to other concepts, and then using this intricate graph structure of your experiences, you can use those to drive decision making. And for this very reason, I claim that graph representation learning is likely going to be a critical component if you want to build anything remotely approaching artificial general intelligence. And as we will hopefully have some time to discuss today, this doesn't really clash with the current state-of-the-art models being used for building artificial intelligence systems, because those systems are secretly graph neural networks, it turns out, and we'll hopefully discuss this connection later. So why are we here? Hopefully, these past few slides convince you that graphs are all around us and that graph representation learning is here to stay. And no matter what field you choose to focus or specialize in, there's a good chance you will come into contact with this field. So I want to make it easy to navigate, leverage, and contribute to. So before we dive into some specifics on how to build graph machine learning models, I would just like us to all be on the same page about what we mean by a graph and what we mean by a graph neural network and so on. So a graph, as you might already know, can be represented as a collection of objects, which we call nodes, and interactions between those objects, which we call edges. And you can usually visualize these structures, sometimes very beautifully, like this Folkman graph here, which is one of my favorite graphs, has a lot of very cool symmetries. And formally, how we detail this is by saying that a graph is a tuple of a set of nodes V and a set of edges E. We typically assume that edges connect two nodes together. So the set of edges is a subset of the Cartesian product of the nodes with themselves. And I should stress that depending on what literature you read or what context you're in, nodes might be referred to as vertices and edges might be referred to as links or relations. For us, all of those terms will be referring to the same concept of nodes or edges. And there's many ways you can represent edges, some more efficient than others, but because in deep learning, we typically talk about things from a context of linear algebra, we are going to be using a linear algebraic representation of edges as well. So we'll be representing our edges with an adjacency matrix, which is a matrix that has a number of nodes rows and number of nodes columns, and all the non-zero entries of this matrix will tell us where the edges are in our graph. And once you have a graph structure like this, you can define various tasks on this graph depending on the scale at which you want to do predictions. You could do predictions on the level of nodes. So say your nodes could be documents connected together by citations, and then a node level task would be to detect the topic of each document. You could also have edge level labels, or even predicting whether edges exist or not, which is a link prediction task, very common in recommender systems. And one typical example of this, you can imagine nodes being drugs and edges drug-drug interactions or negative side effects. And based on this existing graph, you can infer new edges, which basically means forecasting which drugs are likely to interact well or not well with each other. This will be an edge level task. And also, you might predict properties of entire graphs. This is how the antibiotic discovery had been formalized that I told you about before. So in this case, your entire graph might be a chemical compound of atoms connected by chemical bonds. And based on this chemical compound, you might be interested in predicting some chemical property, for example, whether it would be a potent antibiotic or not. If you want to build such machine learning systems, today you have access to a plethora of very useful libraries. So no matter which is your preferred poison of choice, do you prefer PyTorch, TensorFlow, or like myself, JAX? There is a really good graphical deep learning library that you can use to build such systems. For PyTorch, you have PyTorch Geometric or PyG and DGL. For TensorFlow, you have Spectral and TensorFlow GNNs. And for JAX, you have the Giraffe library, which we built internally at DeepMind, and we have released publicly the exact same version that we use internally. So no matter what preferred deep learning framework you use, there is a library that will help you kind of out of the box deploy these graph neural network layers as part of your AI infrastructure. And of course, you cannot have good models without good data. And this is doubly true in graph machine learning because the graph structure gives you an extra level of complexity that you have to account for. Luckily, there's lots of really good efforts to collect both natural and carefully crafted synthetic graph data sets. You can check out the Open Graph benchmark from Stanford, as well as the TU data sets and benchmarking GNNs as some very good examples of this. And lastly, if you haven't played around with these models before and you would like to get started, I always argue that seeing it in action through code examples and good Python notebooks is much better than trying to read a book or read documentations. And just seeing how it works in action. There are luckily great tutorials, regardless of whether you use pure PyTorch or PyTorch Geometric or JAX and Giraffe. There are some really good examples. I will share these links later, but know that there are lots of really good open source and free resources to get a good feel for how these models operate and process a graph structure. Okay. So now that we have covered some basics and some basic pointers that you can use for what you for when you set out to explore data that lives on graphs, let's talk a little bit about how you can actually build models like this. So really, if there is one kind of fundamental takeaway I would like you to take from this session, it is this particular context: permutation, invariance, and equivariance. Now, you might be wondering, what the hell? There's not the word graph, neural, or network in this sentence. I hope that by the end of the session, you will realize that this is actually fundamental to building models, not only on graphs, but also on other data structures. And in fact, these principles underlie models like transformers as well. So where shall we begin? I will actually start with potentially a slight disappointment. We will not start by looking at graphs. We will actually start by looking at graphs with no edges, also known as unordered sets. There's a few reasons why I would like to start from sets. First of all, they're going to be much simpler to analyze because you're only carrying one object rather than two. Most of the conclusions we make will very naturally carry over to graphs. And even though you're only studying graphs, only sets, it is still a very relevant task. So if you have to do anything in computer vision that relates to point clouds or analyzing LiDAR data in, say, self-driving vehicles, as in this Waymo demo on the bottom right, you very often have to deal with sets of points or sets of nodes. So even if we just focus on sets, we're still solving a relatively important problem. So let's see how we can go about building a set neural network. So we assume we have a graph with no edges, so we only have V, the set of nodes. Of course, because we're doing deep learning on this input, we need to somehow featureize it. So we assume xi is a vector giving us the features of node I. And there's many ways you could feed this data to a deep learning model. Typically, what we would do is we would stack these vectors for each node into a matrix, a node feature matrix, which has number of nodes as rows and number of feature dimensions as columns. So the ith row of this matrix will tell you the features of node I. But I must stress that what you've just done there is really, really, really bad because you've specified a particular order of the nodes. And as I told you at the beginning, the set is unordered. So we would like the output of our neural network to not depend on this arbitrary choice. And so let me pictorially represent what we want. So imagine I have a set of 5 objects, x1, x2, x3, x4, x5, with their feature vectors. and I train some neural network, some function that takes into account this collection of objects and predicts a label. What I would really like is to still get that same label, even if I choose to permute the way in which you observe these objects. As long as it's still the same set of objects, I want exactly the same response. Can we force a neural network to do this for us? It turns out you can, and in order to arrive at this, you need to think about what are the operations that would change the order of the nodes. As you might know from combinatorics, these operations are known as permutations, and for n elements, there is n factorial many of them. And what's convenient for us is that within the realm of linear algebra, each permutation defines a unique node-by-node matrix known as a permutation matrix. They are really special. Here you can see an example of a permutation matrix at the bottom of this slide. They have mostly zeros everywhere, exactly 1, 1 in every row and every column. And the only effect that they have is that when you left multiply them with a node feature matrix, it permutes the locations of the nodes and does nothing else. You can hopefully convince yourself of this by just doing a simple calculation. And that's really great because this formalizes the first constraint we would really like our set neural networks to have, which is known as permutation invariance. So we want a function, a neural network f, such that if we apply it to a node feature matrix, it will give us the same response even if we permute the rows. Or put differently, the function of px for any permutation matrix p is the same as function of x. And this is the first important concept, permutation invariance. As long as our function satisfies this, it is a valid set neural network. And of course, this only tells you a constraint. So it tells you something the function must satisfy. It doesn't tell you how to implement that function. And for that purpose, here I give you one implementation, the very popular deep sets model that was published at NeurIPS a few years back. So in this model, what we do is we process the features of every node using a shared learnable function like a MLP, psi. Then we compute the output features for every node and we aggregate them using the sum aggregation. And once we've summed all of the node representations into one vector for the whole set, then we can process it with another function phi to learn whatever output we care about. And the critical part, which gives this model the sum, the permutation invariance property, is the sum aggregation, because sum will always give you the same response no matter in what order you feed the individual nodes. And it also means you can try other things like maximization or averaging. All of these are fair game and they don't modify the order. And for that reason, I often like to not write a concrete aggregator in this function, but rather write this O+, which is just a placeholder for saying any operation that doesn't depend on the order of the operands is fair game here. So whenever you see me use an O+, think this could be a sum, this could be a max, depending on the needs of my problem, I can decide which one works best. Now, permutation invariance is really good if you want outputs on the level of entire sets, but what if you would like answers on the level of individual nodes? Well, you'd still want to be able to identify which output is for which node, but when you do a sum or other aggregation, that is destroyed. So instead, we might need a more fine-grained notion of operations that wouldn't change the order of the nodes. So if you permute the nodes, you'll get a different answer, but in a way that doesn't matter when exactly you permute it. Do you do it before or do you do it after your layer? So accordingly, we get a more fine-grained notion of permutation equivariance, this function capital F of x, which I use capital F to denote the fact that it is now returning another node matrix. And such that for any permutation matrix P, it doesn't matter if I permute before or after applying my function, the outcome is still the same. And this is our second important concept of the day. And another property which is very important besides invariance and equivariance is to also be stable under transformations that are just not the transformations you're looking after, but some general deformations of your input. So you might be designing a convolution neural network to be resistant to shifts in pictures, so it will process this shifted picture of a house really perfectly. But in the real world, your camera will add lots of distortions that will not just be pure shifts, and you would ideally want your model to not collapse in such circumstances. And I don't have enough time to go into the maths of how we resolve this issue, but generally what you want is your signal to be local. So your operations should be local transformations and then compose them to model larger scale ones. And that's the reason why we build convolution networks with only small filters like 3x3, but then we make them very, very deep to model long range interactions. So accordingly, we would like invariance, equivariance, but also some notion of locality. But what does locality mean for sets? Well, really, one way you can do locality in sets is just to transform every node in a set in isolation. So your equivariant layer is just a psi function applied to each feature vector in isolation, and then you stack them together to get the final output. And this really is the first step of the deep sets layer that I showed you before. So this gives us a general blueprint for building functions over sets. You start with an equivariant backbone that processes each node in isolation. And then if you need a prediction in not just the nodes, but the entire set, then you apply this aggregation and final prediction in red. And we can actually prove that this gives us all legal set neural networks. If you wanted to add any additional inputs into this psi, you would effectively be specifying a graph because you would be saying pairs of nodes interact. And with that in mind, we can make the jump from sets to graphs. So now imagine that you have your set of nodes, but also a set of edges between them. And as we said, we will represent these with an adjacency matrix. You could add more stuff to the edges like edge features, but I'm deliberately ignoring them for now to keep the math simple. So what's changed really? The desiderata, permutation, invariance, and equivariance are still very much there. So really, if you remember this picture I showed you before for sets, for graphs, it's really exactly the same picture. The main difference is that now I also have some edges between my nodes. And whenever I permute my nodes, I need to accordingly permute my edges. And that's what I said when I meant it'll be very easy to make the jump from sets to graphs. Really, the invariance and equivariance constraints are the same. The main difference is that now the adjacency matrix is also part of the function, and we need to be careful that whenever we permute the nodes, we also accordingly permute the rows and the columns of the adjacency matrix. So otherwise, it is exactly the same rule as before. Now, the one place where it becomes different is we mentioned invariance, equivariance, and locality. In sets, you could only enforce locality by processing every node separately. In graphs, you have a better notion of locality using the neighbors of each node. So we can define for each node a neighborhood, Ni, which is the collection of all the nodes adjacent to it in the graph. And we can also extract the set of all features in that neighborhood, this Xni. And now our local function doesn't just have to look at xi, it can also look at the features of the neighbors, right? And once you have a good function like this, you can apply it to every node's neighborhood in isolation, stack the results, and get your equivariant graph neural network. The main constraint you have to be careful about is because this function phi now looks at the multi-set of neighborhood features, you need to be careful that phi is invariant in the neighborhood features so that the whole function f will be equivariant. It's a good exercise to try to do a small algebraic manipulation to try to prove this, but this is really the recipe of how we build all GNNs. And I realized that the previous slides might have offered a lot of mathy introduction to the area. It might be good to occasionally see a picture of what all this means, and this is exactly what it means. So everything I've been telling you about so far set us up for this. A graph neural network is no more or less than a function that looks at features of a node and features of its immediate neighbors in a graph and predicts updated embeddings. And then you can stack a bunch of layers like this to predict whatever you want over a graph. So let's say I have general graphs with inputs xi features in the nodes and adjacency matrix between those nodes. As we discussed, I run my GNN over this graph to update my nodes in some latent space in a way that depends on my immediate neighbors. What can I then do with these h's? If I have to predict node properties, I can classify each of these h vectors using a node classifier. If I have to predict entire graphs, I can build a graph classifier, but I need to be careful that my prediction is invariant to the order of the nodes. So I must first aggregate my node features together, then feed that to a graph classifier. And I can also predict stuff in the edges or edge existence by classifying features of the two nodes that are relevant for that edge, and maybe any additional edge features if I have them. And this slide, I would argue, describes 99.9% of discrete deep learning applications today. Almost all of the big applications I told you about previously can be seen as one of the three pathways inside this slide over here. And I still haven't told you how to implement this local function phi, and it's a super intense area of research, but fortunately you can classify almost all of them across these three spatial flavors, which look like this: convolutional, attentional, and message passing. Here I've just listed them for reference. As you go left to right, they get more strong, they overfit more easily as well, and it's really hard to find the right balance sometimes. You have to try all three of them and see which one works. The attentional version, which is kind of a middle ground, is very, very important. In fact, transformers are a special case of an attentional GNN, so maybe it should come as no surprise that they offer a sort of middle ground between full expressivity and full scalability. Now, we are reaching the end of the talk, and I must stress that there's a lot of very fun content I would have loved to tell you about how to implement the three flavors, where do they come from, how to deploy them in interesting applications, but I only had time for this much today. So if you would like to know more, I have published a recent survey paper on everything is connected graph neural networks, and also a publicly available talk on the basics of GNNs that I've put on YouTube, Theoretical Foundations of GNNs, which has over 70,000 views on YouTube, and it has been well battle tested by the community. I would argue it's a good way to introduce yourselves to the field. So this is where I will stop. Thank you very much for attending my talk, and I'm happy to take any questions you might have.